13.3 is called pendulum energy. So we've got our pendulum shown there. We have a graph of horizontal position versus time. One end of a string is secured to the ceiling of a classroom, and the other end of the string is attached to a sphere. Mass 0.2 kilograms, so that a pendulum is established. The sphere is raised at an angle of 15 degrees above the sphere's equilibrium position. Let me stop for a second because we've seen that number a few times in these FRQs. Remember that that was sort of our parameter for simple harmonic motion. The angle that the pendulum makes with the vertical can't be much more than 15 degrees. And if you remember, the reason we did that is because the restoring force is actually proportional to the sine of that angle, and we can't really use it properly. We're making the assumption that the sine of the angle is actually equal to the value of the angle for radians. If you don't remember that, you might want to look that up or ask me about it. But it's important that we have small oscillations here. Location 1 is shown in the figure. It looks like it is over to the left. A graph of the pendulum's horizontal position as a function of time is shown. So the dot below represents the sphere at location 2, which is straight down. We're going to draw a free body diagram that labels the forces exerted on the sphere at the bottom, and we're going to draw the relative lengths of all vectors. Now, this is the first time we've seen this, and again, you're not going to have to draw it on the test, but I did just see a multiple choice question somewhere where you had to figure out which free body diagram was correct and the lengths of the vectors mattered. So that's why we're practicing. So the free body diagram, we've got gravity acting down, and we've got tension acting up, and the tension vector is longer, and the reason is because the pendulum is moving in a circle, so there's a net centripetal force, so the tension in the rope is bigger than the weight at that point. So you'll want to make sure that when you do this yourself, you draw it longer. And like, if we were actually doing this, we'd do it on a grid, so you could just do it 4 ticks instead of 3 or something like that. But then even I wrote the word longer on mine just so that I could be clear. This one I mean to be longer. So 2 points there, 1 for an upward tension and a downward gravity vector, and 1 point for realizing that tension has the larger magnitude. All right, on to part B. Calculate the maximum kinetic energy of the sphere as it oscillates, So I figured that I could find the period of, I could use the period of rotation to find the length of the string. Okay, because that's not given to me. So I used the period of the oscillation, to find the length of the string, and it's about 1 meter. Okay, and then remember, we've done this before. This is the height drop, right? It starts here and it ends here, so we're going to do an MGH equals 1/2 mv squared. But what's our height drop here? Well, if this is 1 meter and that's 15 degrees, okay, then this is 0.966 meters, right? And my height drop then is 0.034 meters. I've drawn sort of an exaggerated triangle. My angle is almost 45 degrees, so it's a lot more squished than I'm actually saying. So here's the height drop, this 0.034 meters. So we've got MGH equals 1/2 mv squared. Over here, we've got H of 0.034 meters. The masses cancel, even though we actually know the mass of the bob. It's not a big deal. They only ask for the kinetic energy, so we don't actually have to find the speed. So this here, this MGH, I guess we do need the mass there. That's equal to 0.068 joules. So we didn't actually have to find the speed. We could just equate that to the initial potential energy, which is 0.068. So we have 1 point for using the period to get the length of the string. 1 point for getting this 0.966 meters. It's L minus L cosine theta, if you remember how I did that before. If not, let me know. And then once we find this delta H, we use the mg delta H to find the maximum gravitational potential energy, and then we just make that equal to the kinetic energy. So I know I circled a lot of things there, but 2 points there. On to part C. Explain, the sphere is raised to a new angle above the sphere's equilibrium position that is less than the angle described for part A, less than the angle described. The sphere is released from rest so that the pendulum oscillates. Explain how the motion of the sphere changes, if at all, based on the appropriate evidence. Well, if all we did was change the angle of oscillation, nothing is going to change, okay? The amplitude changes in that the highest point that it reaches changes, but nothing else. So the period remains the same because only the length of the string and the gravitational field affect the period. So I don't think you would be wrong if you said the amplitude of the oscillation was less, because that's correct, but there's not anything with that in the rubric. 1 point for saying the period remains the same, and then 1 point for explaining that only the length and the gravitational field affect the period. So 2 parts for point C.